Hello, this is group number 1 and we'll talk about section 3.2 equivalent diameters for non-circular ducts. Non-circular ducts are found in a number of fluid systems. Rectangular and square cross-sections are used for air conditioning or heat ducts. Annular cross-sections are found in double pipe heat exchanger where one tube is placed within another. The section between the tubes is annular. The question is, where should be used for the characteristic dimension of the non-circular duct? 3 different choices for characteristic dimension have been proposed, and we will define each of them.
In order to find pressure drop in a non-circular conduit, we have to find hydraulic diameter. The hydraulic diameter is 4A over P. In the figure as shown in the screen is a double pipe, which is a pipe in a pipe. We take the difference in the areas of the outer pipe inner diameter and the inner pipe outer diameter, and we sum the perimeter or where the fluid is touching, and then we plug in those values into the hydraulic diameter equation. Going on to the next slide, we have a square conduit. We have the equations for perimeter and area, and then we plug those values in for the hydraulic diameter, and we have the hydraulic diameter of the square conduit.
Second, we will talk about the hydraulic radius. The hydraulic radius is often used for systems with free surface flow, such as water in open channels, streams, or rivers. We define this by R sub of H is equal to the area of the flow divided by the weighted perimeter. For example, as you can see, we got an annual cross-section bounded by 2 tubes. For the area of the flow, we calculate the area of the outer tube using its inside diameter and subtracted by the inner tube using the outside diameter. As for the weighted perimeter, we just add both. By calculating those 2 values, we divide the area by the weighted perimeter and we get the hydraulic radius.
The effective diameter is also known as the equivalent diameter. It's an approximation of a circular duct area to a non-circular duct area. It is not efficient to use for fluid applications and mostly is used in heat transfer applications. Here we have 3 examples. On the left we can see circular ducts, and on the right we can see 3 shapes: square, a triangle, and an ellipse ducts. Comparing both areas to each other, we can solve for the effective diameter.
On this slide, we demonstrate how to calculate the hydraulic diameter, hydraulic radius, and the effective diameter. On this problem, we're given that the inner tube is a 2 standard and the outer tube 4 standard, both type K tubes. To find these values, we use the table D1 to find the inner diameter and the outer diameter of each pipe. To find the annual floor area, we simply find the difference in area of the inside diameter of the second tube minus the outside diameter of the first tube. The perimeter is found when we add the inside diameter of the second tube plus the outside diameter of the first tube times pi. Hydraulic radius is found by applying the equation area over perimeter. And hydraulic diameter is found by 4 times A over the perimeter. And the effective diameter is found on the square root of 4 times the area over pi.
For problem G19, we are given that the pipe is made out of 1/2 standard type M copper tubing. There is 12.2 meters of tubing, and the velocity can be no less than 2 meters per second. The liquid is benzene, and the power is distributed evenly. All fittings are soldered together. The pressure drop in the inlet is 27.58 kPa. Starting the problem, assumptions that we have is it is incompressible along the streamline in steady state. Its horizontal alignment and potential kinetic energies are negligible due to the same height for pressure sensors. All fittings are soldered and flanged. We're given a velocity is 2 meters per second. The density for benzene is 876 kilograms per meters cubed. Viscosity is 0.6 10 to the negative 3 newton seconds meter squared. The length of the tubing is 12.2 meters, and the delta P is 27.58 kpsa. The diameter from the tubing we gotten from table D2 is 1.46 centimeters, and the cross-sectional area is 1.64 centimeters squared. The roughness factor for copper tubing is given in table 3.1, and it's at 0.015 millimeters. From table 3.2, we can get the loss coefficients for KE, which is bends, and KR, which is returns. And KE is 0.31, KR is 0.3. Having a K equivalent of 2 bends and 7 returns, equal total is 2.72. We're not accounting for K for entrance and exit as an assumption that the heat exchanger is connected directly to the pipes. From this, we can figure out the Reynolds number. It's 42,000, which puts it in a turbulence region. Using the formula for the Moody diagram, we find in the friction factor being 0.022. So we're looking at modified Bernoulli's equations with a delta H for total head, with V1 equal V2, the velocity is along the same pipe diameter, Z1 equals Z2. We can drop those out and solve for delta P. We are left with minor loss, major losses, and delta H. We solve for delta H and find it out after substituting the numbers that it's 1.144 meters. We know that power required to the fluid is equivalent to mass flow rate times gravity times delta H. From that, we find out that the power required is negative 3.226 watts. It is negative because the power is provided to the system.